Let's now take a look at the concept of the photoelectric effect. When light strikes a material, you have incident light striking a material. Somehow, the incident light induces the electrons in the material to be emitted. This phenomenon is referred to as the photoelectric effect. Halwax and Leonard showed that not always electrons will be emitted. You, you need to have an incident light of sufficient frequency. Halwax and Leonard showed that when the frequency of the incident light is greater than what is referred to as a threshold frequency, which will depend upon the material, that's when the electrons or photoelectrons are emitted from the material. So incident light must be of sufficient frequency to induce the electrons in the material to be emitted. The setup used by Halwax and Leonard basically consists of electrodes, two electrodes, anode and cathode, connected to a power source. Incident light strikes one of the electrodes. If the incident light is of sufficient frequency, if it's greater than or equal to a threshold frequency, particularly if it's greater than a threshold frequency, electrons are emitted, and the kinetic energy or the initial speed of the electrons may be measured by adjusting the potential difference across the electrodes. The initial kinetic energy of the emitted electrons, 1 half mv squared, 1 half mv squared. M is of course electron mass. V max is the maximum initial speed of the electron. And by varying the potential, V naught, by varying the potential across the electrodes, by varying the power source, say if you increase the potential, the positive side becomes more positive, the negative side becomes more negative. The positive side will attract the electrons, the negative will oppose the electrons. You have will repulse the electrons rather. Eventually, there will be a value for the potential wherein the electrons are no longer able to reach the other electrode. There will no longer be a current flowing in the circuit. That value of the potential is basically V naught, referred to as the stopping potential or voltage. 1 half mv squared is equal to EV naught. Einstein postulated in his paper on photoelectric effect that a beam of light consists of small packages of energy called photons, that if you turn on a flashlight, the beam of light produced consists of small packages or particles of light referred to as photons. The total energy of the beam of light is the summation of the energy of each photon. The energy of each photon is E is equal to HF is equal to Hc over lambda. F is the frequency of light, lambda is the wavelength of light. This explains, E is equal to HF basically explains the observation by Halwax and Leonard that the incident light must be of sufficient frequency to induce the electrons into being emitted. If the beam of light is of sufficient frequency, meaning the photon energy is of sufficient frequency. When the photons are absorbed by the electron will gain enough energy to be able to escape from the material to be emitted by the material. We have EV naught is equal to HF minus phi, where phi is referred to as the work function. It depends on the material. It's basically the minimum energy needed to remove an electron from the surface of a material. So, if the incident light has a frequency greater than the threshold frequency represented by the work function, the extra energy will be the kinetic energy of the electrons. The electrons are thus able to escape from the material, from the surface of the material. So EV representing the kinetic energy of the emitted electron is equal to energy of the incident photon, minus the work function of the material. C, of course, is the speed of light, 3 times 10 to the 8 power meters per second. H is Planck's constant. The photoelectric effect points to the dual nature of light, that light behaves both as a wave and as a photon, as a particle. As a wave, it has wavelength and frequency. As a particle, as a photon, it has energy hf as well as momentum p. P is equal to E over C is equal to hf over C is equal to h over lambda. In fact, that's the condition for a massless particle like a photon to exist. For a massless particle to exist, it must have both energy and momentum. So that's it for now. We'll continue our discussion of atomic and nuclear physics in the next video. Thank you for watching.